Hi, everyone. I am Rebecca Wright, Chair of Computer Science at Barnard, and welcome to our Computer Science Seminar. We are very happy to have Dr. Elaine with us today. She is a faculty fellow at the Barnard Institute at NYU and is interested in logic, automata theory, and formal verification, and will be talking to us today about her work in that area. She obtained her PhD in computer science from NYU in 2025, as well as her Bachelor's of Science from Yale and US National University of Singapore College in 2019.
Thank you for the introduction. I'm very excited to be here today to tell you about my work on abstractions for building verified distributed systems. So distributed systems are ubiquitous in modern society, and we increasingly depend on them for a variety of applications, from managing financial transactions to predicting the weather, to even in some cases, administering life-saving healthcare. Bugs, on the other hand, in concurrent and distributed systems can have severe consequences, ranging from, on the mild case, a feeling like your favorite websites keep going down, to nationwide power outages that affect large swaths of the population, to even, in the most severe of cases, a loss of life. The most recent issue of the Communications of the ACM estimated that the engineering cost of fixing poor quality software in general exceeds $1 trillion in the US alone, with cybercrime that aims to exploit software bugs itself being another $8 trillion a year business. So software is everywhere. It can be mission and safety critical, and software bugs can have severe consequences. And what is the industry doing about this? By and large, they're doing testing. So if this is the universe of possible behaviors of a piece of software or a program, we can divide these up into a set of good behaviors, with the remaining ones being bad behaviors. And our program behaviors also live in this universe. What testing does is that it manually examines a finite test suite of behaviors and checks that each one of them is good, considering factors such as coverage of the code, as well as making sure to include corner cases. But fundamentally, testing cannot distinguish between this happy scenario, where all of the program behaviors are in fact good, and this scenario where all of the inspected behaviors are good, but there are some program behaviors that are bad, but that have not been caught by the test suite. And as pithily summarized by Dijkstra, program testing can be used to show the absence of bugs, but never to show their absence. When the underlying program is a distributed system, this is perhaps a more representative visual of its behavior. Even when a bug has demonstrably occurred, they can be difficult to reproduce and diagnose. And this was, in fact, the case with the recent November 18th Cloudflare outage. So on the y-axis, we have number of server errors in terms of million requests per second. And on the x-axis, we have time. And I want to draw your attention to this middle section where you have an oscillation in the number of server error requests that led the engineers to suspect at some point whether the system had recovered on its own, or even whether the outage was the source of a malicious attack. And this kind of unpredictable behavior inherently arises from the non-determinism that's characteristic of distributed systems, and further points to why testing in general doesn't suffice as a means for detecting bugs. So this points to the need for a more principled and powerful solution. And luckily, the CACM proposes a viable, if not the only solution, and that is formal verification. So unlike testing, which examines finitely many behaviors, formal verification precisely models the behavior of a program in mathematical terms. It formally specifies what correctness means, usually as a logical formula or some other abstract specification. And then it makes use of mathematical reasoning to establish that the potentially infinitely large set of program behaviors are a subset of the formally defined correct behaviors, often denoted by phi. So formal verification has seen some successful adoption in the industry, with applications including microprocessors fault-tolerant algorithms and cryptographic libraries being verified on an almost routine basis. Unfortunately, there is one application domain that's conspicuously missing from this list of applications, and that is distributed systems. This is not for lack of trying, however, and during my PhD, I spent 2 summers at Amazon trying to scale distributed systems verification to a point where it could be widely adopted by industry. So during my internships, I verified the core concurrency control protocol behind the Amazon Aurora database that is used by over 10,000 companies across the world using a verification tool called Daphne. Using my experience there as a starting point and generalizing the field more broadly, these are the 2 challenges that I believe are outstanding between us and wide-scale adoption of distributed systems verification. The first is that we want to verify systems at the right level of abstraction. On the one hand, verifying low-level code is very challenging and messy. On the other hand, verifying abstractions without connecting them to implementations doesn't serve the right purpose. The second is that we want to verify systems in situ with implementation, meaning that verification cannot be an afterthought after the system has already been implemented and deployed. My research uses techniques from automata theory to address both of these challenges. And in the first part of my talk, I'm going to describe my PhD work, which focuses on a particular abstraction, that of global protocols. I'm going to show how we use a novel automata-theoretic lens to improve upon the state of the art along the dimensions of completeness and expressivity without sacrificing efficiency. In the second part of my talk, I'm going to describe ongoing and future work on making verification techniques for distributed systems more compositional and incremental. So let's take a step back and consider how we would go about building distributed systems. So let's suppose we have 3 participants, a seller and 2 bidders, and these 2 bidders want to come together to figure out the fair split of the cost of a book that they both want to buy. So being distributed across time and space, the only way these participants can communicate is by sending one another messages. And message passing is the cornerstone of building distributed systems. Communication protocols are what describes the message passing behavior between participants in a distributed system. And what this means is that for each participant, I would need to write a local implementation that describes for each participant how messages are sent and received. And at the local implementation level, I want to enforce certain aspects of my protocol logic. For example, for each bidder, I might want to enforce that they make strictly increasing bids. For the seller, I want to enforce that the book is only released if the sum of the 2 bids indeed exceeds the price of the book. So I would write such an implementation that locally enforces these aspects. And then ultimately, I need to throw my implementation onto an asynchronous network that handles the actual message passing. This asynchronous network turns out to be the primary source of bugs in distributed systems. And that is because the asynchronous network can arbitrarily delay and reorder messages in flight, which means that this can induce a large class of communication errors, including orphan messages, messages that are sent but never received, unspecified receptions, or messages that arrive out of order and are not anticipated, and can even cause system-wide deadlocks. So as a developer of the distributed system, not only do I need to worry about correctly implementing my protocol logic, I also need to worry about avoiding these potential sources of communication errors that arise purely from the network alone. And this is a lot for me to worry about at once. What would be nice is if I could push a button and synthesize correct by construction implementations automatically from some kind of abstraction that gives me this illusion of a separation of concerns between the protocol logic and the communication layer. So meaning that the protocol designer can focus on capturing their intent without having to worry about low-level possible communication errors. We might like an abstraction that, for example, gives us the illusion that there are no message channels. So messages that are sent are received immediately, and therefore cannot be delayed or reordered with other messages that are in flight. They might also like to help ourselves to the illusion that there is an omniscient coordinator that can see the local state of all of the participants and sequentially execute interactions between all participants in a distributed system. It turns out that this is a quite natural idea for an abstraction, and in fact, these abstractions have existed in the form of what we call global protocols as a blanket term since at least the 90s, where they were introduced in the form of high-level message sequence charts. Global protocols are also at the center of two very active areas of programming language research, namely multi-party session types and choreographic programs. Global protocols have been integrated into several languages that are used in the industry, including the ITU standard, universal modeling language, and have been applied to a variety of domains beyond just distributed systems, including, for example, cryptographic security protocols. And the exact form that these global protocols take differs a bit according to the area, but in general, they all share some key characteristics. And I'll use the visual formalism of a high-level message sequence chart to illustrate these features. So the first is that the behavior of all participants is specified jointly. So in this diagram, each vertical line belongs to one of the three participants, either the seller, bidder 1, or bidder 2. And the horizontal arrows that go between the vertical lines describe message exchanges. In particular, the arrow describes the sending and receiving of a message atomically, so assuming that both of these actions take place at the same time. There is one global control flow for all participants in this distributed system, and these black outer boxes and these thicker arrows describe the global control flow. All participants are assumed to move through the control flow at the same time. Finally, in the case of this example, our transitions or our message exchanges are annotated with logical predicates that allow us to express things like bids are made in strictly increasing order. So in this transition or message exchange here, the message being passed is denoted by variable B1, and the predicate, which says B1 is greater than C1, describes that the bid made has to be greater than the previous bid, which is stored in the form of a loop variable. So these global protocols feature these rich programming language constructs that you would expect, such as looping and recursion, and you can also denote terminating states using these double-lined boxes. And furthermore, these global protocols can be used as a specification directly from which we synthesize local implementations, one for each of the participants, that when you throw them onto an asynchronous network are guaranteed to not exhibit communication errors and correctly implement the desired protocol logic that's captured at a high level by the global protocol. So this all sounds good, and are we done here? Well, it turns out no, because anytime you want to solve a synthesis problem, you have to first solve the realizability problem. So in our setting, the global protocol made use of two illusions. The first illusion is that there are no message channels, and the second illusion is that there is a global coordinator that can sequentially execute all participants' interactions. Neither of these illusions is true in a purely distributed setting. So the realizability question, in our setting we call implementability, asks, given a global protocol, does there exist a distributed implementation that can in fact correctly realize its intention? So let's take a look at some examples of non-realizable protocols. So here we have a very simple protocol. It involves, again, three participants. Let's call them P, Q, and R. And from the global protocol designer's perspective, this protocol has just two scenarios, an orange scenario on the top and a purple scenario on the bottom. And in each scenario, participants pass messages that match that scenario's color. But if we take a closer look at the message passing pattern inside each scenario, we'll find that the first action of each scenario is that P communicates to Q, the color denoting scenario, after which R, who has no knowledge of P and Q's interactions in a distributed setting, is expected to send the same color message that matches the message that P sent to Q, also to Q. Of course, R has no knowledge of the message that P sent to Q, and so R cannot avoid exhibiting behaviors that violate the protocol designer's intent by sometimes sending messages that does not correctly match the color of the message that P sent to Q. This is just a protocol with two kinds of messages, an orange and a purple. When we write protocols that feature logical refinements with variables that can denote infinitely many behaviors, these kinds of non-implementability patterns are very easy to run into. So in this protocol, we have, again, three participants, P, Q, and R, three variables, X, Y, and Z. So P first sends to Q a message containing a value denoted by X. Q then sends to R a message containing a value denoted by Y, with the constraint that Y is greater than twice of X. After which R sends to P a message Z with the constraint that Z has to be greater than X. So of course, R does not learn the value of X from the communications. It can infer something about X through the value of Y, but it is not able to exhibit all of the satisfying values of Z, in particular the ones that are between X and half of Y. So for this reason, this protocol is non-implementable because R cannot exhibit all of the intended behaviors by the protocol designer. A typical way that prior work would try to catch this issue is by syntactically classifying the variables in the protocol into ones that are known and unknown. So a variable is known to a participant if they either sent or received it, and it is unknown otherwise. So based on this, X is known to P and Q, Y is known to Q and R, Z is known to P and R. However, in this third message exchange between P and R, it concerns a variable X that is not known to R, and so such methods would label this protocol as being non-realizable. This syntactic classification method is insufficient because I can easily exhibit a protocol that has the exact same classification of known and unknown variables, but that now is implementable. In particular, all that I have done is change the predicate y greater than 2x to y is equal to 2x. So now R is able to infer exactly the value of X and send all possible values of Z that satisfy its transition constraint. So to get a better sense of what realizability is really about, let's look at two possible executions of this non-realizable protocol. So the possible execution concretely instantiates the variables X, Y, and Z with integer values. So in the first execution, we have X being instantiated with 2, and in the second, X is 3. Hopefully these are visible. Okay, so first, P sends to Q either 2 or 3. Okay, after which I'll pick the value of Y to be 10 in both cases, which is satisfying because 10 is greater than twice of 2 and twice of 3. And now when it comes to R's turn, so R has observed the same behavior in both of these scenarios. All it has observed is receiving 10 from Q. However, in one scenario, if R were to send 3 back to P, this would follow the protocol. However, in the other scenario where X is set to 3, sending 3 would constitute a violation because 3 is not greater than 3. The issue is that R cannot distinguish these two scenarios based on the information that it receives in this distributed setting, which is just to receive 10. So hopefully this idea of executing two traces in parallel hints you towards the idea of hyperproperties. We distilled this intuition for characterizing exactly when global protocols are realizable into a set of 3 hyperproperties that we call the coherence conditions. These coherence conditions say in a nutshell that when a participant is in 2 states that are locally indistinguishable to it, it can either send a message that is permissible from both states and thus continue to not distinguish them, or it can receive a message that uniquely distinguishes one state from the other, but in the presence of uncertainty, it cannot choose between either sending or receiving a message. We show that these conditions are sound and complete with respect to implementability. So a protocol is implementable if and only if it satisfies these three conditions. And the way that we develop these conditions is through an automata-theoretic lens. So another way to view these hyperproperties is as reachability conditions on a product automata over the global protocol when also viewed as an automata. So through this automata-theoretic lens, we were able to devise the first precise solution to implementability. So implementability is slightly subtle to figure out. The good news, though, is that once a protocol is implementable, the synthesis problem becomes very easy. And again, in automata-theoretic terms, amounts to a simple modified subset construction. And I can show you the synthesis algorithm all on one slide. So here is a global protocol. You'll notice that the alphabet labels talk about interactions between all pairs of participants. So the alphabet contains, for example, PQ interactions as well as RQ interactions. If I want to synthesize the local implementation for R, let's say, what I first do is look at only the transition labels that concern R. So R is either sending or receiving. And I apply a simple alphabetic homomorphism onto the automata to only retain the labels that concern R, bringing all other labels that don't concern R to epsilon. And then finally, I extract whether R is doing the sending or receiving, so either one of the two. So now this is an automaton over a local alphabet that concerns only R that has epsilons in it. So in the final step, we apply a simple determinization algorithm, and now we obtain a implementation for the R in the form of an automaton over its local alphabet. And we repeat this process for all of the participants in the global protocol. Once we have a candidate implementation for a realizable or implementable global protocol, we may also want to ask whether it can be replaced in part or in whole with a different implementation for the purposes of flexibility or concision. And it turns out that these problems can also be recast as reachability problems in the underlying automaton. So it turns out that this view has been fruitful, and it allowed us to derive a series of results, and I'll tour you through some of the highlights. So the first is that it enabled us to devise the first sound and relatively complete algorithm for deciding implementability for infinite state protocols. And we implemented this algorithm in a tool called Sprout. And I'll show you Sprout's delta over prior work in terms of two evaluation figures. So we benchmarked Sprout against its most comparable tool in terms of expressivity. This is a tool from the multi-party session type community called Session Star. And we compiled all of the benchmarks from the literature to benchmark Sprout against. And unsurprisingly, because Sprout targets a richer and more expressive class of protocols, Sprout is able to express and correctly classify all of the examples taken from the literature. However, you'll notice that all of these examples are implementable. So the ground truth implementability is yes for all of them. And what this means is that we're not able to use this benchmark suite to assess the precision of the two tools, in particular, completeness, which asks for non-implementable protocols, do the tools correctly reject them as being non-implementable? So to address this, we augmented the benchmark suite with a set of new examples. For each example, we introduce a perturbation that results in a non-implementable version of the same protocol. So with this, we're able to express precision, to assess precision. And you can see that Sprout correctly classifies all of the examples that it doesn't time out on. These are denoted by question marks, whereas its competitor almost ubiquitously rejects all of the new examples as being non-implementable, despite the fact that the split is about half-half. Finally, in terms of efficiency, Sprout implements a sound and complete algorithm, whereas its competitor is only sound but incomplete. Nonetheless, Sprout performs on the same order of magnitude for most of the examples that we tested. Okay, next, we also used this lens and our characterization to derive the following complexity results for finite protocols. So we show that for protocols with logical refinements over a Boolean theory, the implementability problem is p-space complete. For explicitly finite protocols, so finitely many states and transitions, implementability is co-NP complete. And for the subset of finite protocols that correspond to multi-party session types, which are syntactically defined fragment, implementability remains co-NP complete. And what these complexity results allow us to do is to show that prior work's attempts to solve implementability and synthesis together using linear time algorithms have an unavoidable source of incompleteness. So let's see an example of a protocol that could not be correctly classified by prior linear time algorithms. So in this protocol, we again have 3 participants, so P, Q, and R. And again, P initiates the protocol by sending either an orange or a purple message to Q. If it sends an orange message, then Q will forward that orange message to R, after which in both of the branches, the protocol enters the same loop. In the loop, P sends an orange message to Q and Q forwards it twice to R. After an arbitrary number of loops, P can decide to terminate, and it does so by sending a blue message, termination signal, to Q. Q will forward that termination signal to R. At the very end of the protocol, R is expected to demonstrate knowledge of the initial message that P sent by sending back a message whose color matches the initial message. Okay, so let's look at what the implementations for P, Q, and R respectively would look like. So in this protocol, P is the decision maker. P chooses initially which of the left or right branches to take by sending either an orange or a purple message. P chooses how many times to loop through this middle body. And finally, P chooses when to terminate the protocol for everyone by sending the blue termination signal. So it should be fairly intuitive that the state machine, that the automata implementation for a Q largely resembles the structure of the global protocol. Q does not make the decisions, but Q is P's right-hand man. So anytime P makes a decision, they communicate it to Q immediately, right? P tells Q about the initial choice. P tells Q when to terminate. So for Q, the implementation is also straightforward, except that we have this loop in the middle that collapses because Q performs the same actions in the middle body for both of these branches. The interesting participant to consider is R. So R neither makes the choices like Q, nor does R learn about the choices from P. In fact, if you look at what R is doing in this protocol, it seems that all R is doing is just receiving some number of orange messages. At the end, it receives a blue message, prompting it to demonstrate knowledge somehow of the initial choice that P made by sending either an orange or a purple message. It turns out that this protocol is in fact implementable for R. And the way that R can divine the initial choice of P without being told explicitly is by tracking the parity of the number of orange messages that it receives. So in the case that it receives an odd number of orange messages, it knows that everyone is on the left branch. And if it receives an even number, it knows that everyone is on the right branch. And these transitions here that are highlighted in yellow represents that each time R receives an orange message, it flips its belief state from the left to the right branch, so that when it ultimately receives the blue message, it's able to send the correct corresponding message color that matches P's initial message. And the implementation for R that includes such transitions cannot be synthesized by a linear time traversal. Okay. Finally, we mechanized our core result in the rock prover. So this is an interactive theorem prover with a very small trusted computing base. For this reason, mechanization is often considered the gold standard in formal verification. And mechanization basically entails making a proof precise and small step enough so that its validity can be checked by an algorithm, specifically by the compiler of the ROC, your improving language. So this concludes my discussion of my PhD work. And in the next part of the talk, I want to describe ongoing future work. And I want to do so by first taking a step back and looking at the area of distributed systems verification as a whole. So I really enjoy working in this area because to me, it represents a perfect marriage of two fields, system and theory. So on the system side, there is large potential impact for practical adoption. And on the theory side, all of these verification tools and frameworks are built upon core pillars of theoretical computer science. For example, automata, which I've talked about extensively, as well as logic and type theory. And in the beginning phases of distributed systems verification, we were concerned with what I would call first order concerns. So are our verification tools sound? If it's verified, does it mean that it's correct? Are the tools efficient and practically usable and tractable? Are our verification techniques expressive enough, both so that we can capture realistic distributed systems and also so that we can prove a rich class of properties beyond just, let's say, absence of communication errors, but including properties concerning performance, let's say. And finally, not as strictly necessary, but nice to have, are our tools complete? So do they return false negatives, which could be frustrating for a developer to interface with? I believe that the field of systems verification has reached a point of maturity where we can now start to think about second order concerns. And these are things like tool maturity. And one particular tool that was released this year that excites me is a tool called Veil. So Veil supports both automated and deductive verification seamlessly within the same ecosystem. And it's built on top of the modern theorem prover that's been receiving a lot of attention lately called Lean. The two particular second order concerns that I want to focus on in my future work are incrementality and compositionality. And I hope to explore other areas of automata theory and logic in order to address these concerns. So to motivate why incrementality is important because the process of developing systems itself is incremental. So let's suppose that I want to build a distributed system that handles some centralized database. I might start by implementing the core functionality, which is the concurrency control protocol that guarantees us some isolation properties like serializability or snapshot isolation. I might then layer on top of that a leader election protocol that now makes my protocol tolerant to failure. So for example, instead of one node being responsible for each key in the database, instead we have a cluster of nodes. Any of them can fail, but at any point there is a leader that handles transactions. For performance reasons, I might want to layer on top of that a caching protocol that describes how transaction reading and writing is batched to achieve better efficiency throughout the whole distributed system. And with system development being this way, what we don't want to do is for every time we modify the overall program or protocol to have to redo our correctness proof. My proposed solution to this is based on the observation that while the program or protocol key may change frequently, we expect that the correctness specification phi changes with much less frequency. I envision a verification approach where we focus more of our efforts on pre-processing the correctness property itself. So we prove some meta properties about phi, for example, that it is agnostic to certain kinds of transformations in the underlying program or protocol, such that when the protocol changes, we can construct a much simpler proof that exploits these invariance properties. And this nugget of an idea, again, appears perhaps unsurprisingly in a very old paper on formal language theory that was authored by Elaine and Wolper, called an algorithmic approach for checking closure properties of omega regular languages. And this paper basically shows that when your property phi and your program are simple enough, that this invariance meta property can be decided in p-space. Another reason that I love automata theory is because I believe it is very accessible for undergraduates to get involved. And I myself am a living example of this. So this was a paper that was based upon my capstone thesis that was completed at Yale and Yost College with a very uninterpretable title that I've since annotated. So pumping with or without choice means block pumping, which are a collection of ways of characterizing regularity in languages. And with or without action of choice means that we propose a constructive algorithm for a formally classical. Okay, so I want to end by taking a further step back. As a researcher in programming languages, my job is to design abstractions that make programming easier and more secure for all. And the keyword here is really design. So we design abstractions and verification methods around these abstractions that have an end user in mind. And up until this point, that end user has been a human programmer. So we design abstractions, for example, with the global protocol that make it easy for humans to avoid having to reason about concurrency, which we're inherently bad at, and instead express things in a sequential manner that sort of hide away the concurrency. In my view, there is no reason that we cannot apply the broad scientific methodology and principles of programming languages research as a whole to instead design abstractions with an AI user in mind. And some initial steps in this direction that excite me are, for example, a lot of neurosymbolic programming techniques where formal verification is combined with large language models to generate programs that provide stronger guarantees of their correctness. So this can be short-term in terms of making, for example, feedback from existing framework and tools more interpretable to AI, or in the very long term, designing blank slate abstractions and verification techniques that put a possible AI user front and center. So with that, I would like to conclude. My research is about using automata-theoretic techniques to build reliable distributed systems, and I look forward to your questions.
We can take questions in the room and on the Zoom, and the way the audio is working, we should be able to hear the Zoom people and they should be able to hear our questions. So you don't need to repeat questions, and I'll keep an eye on the Zoom for raised hands or chatted questions. So any questions?
Do you know, are you familiar with eBPF in the Linux operating system? So it's a little similar in terms of just the verification of allowing people to plug in custom code. It has to run through a runtime verifier in the kernel. I'm just wondering, this all seems design time, but do you think that there would be a way to have this be more dynamic, and as you change a system, like how to make it a little more runtime verifiable?
Right. So I think verification people typically think of sort of compile time and runtime, like there's a big barrier between them, right? Because especially for a lot of programs and systems that are deployed, you really don't want to only catch the bug after the system is already up and running. So my work has focused more on sort of pre-runtime techniques, but one interesting direction in this area concerned updates to distributed systems. So this kind of has this awareness that you can't just expect a system that is deployed to never be changed. And so there are interesting challenges that arise with how can we keep the system running, but have formal guarantees about our updates so that things don't break.
Neural network verification, they, I guess, have the same thing where they go between, I guess they want to verify, but they also could do testing in the same way you might do testing in distributed systems, but neural network verification, they run into the bottleneck that they can't really do large neural networks. Is there any scalability issues in verifying distributed systems that prevent this from being adopted widely?
Yes. So in the sense that for even finite protocols in this sort of simplified abstraction that I present, the complexity is pretty bad, right? CoMP is kind of undesirable. I've seen works that are in the area of using, for example, SMT solvers to verify neural networks. And there you can really only verify very small neural networks in terms of like the total number of nodes. So there's also another sort of different methodology that's less foundational, but that focuses on developing heuristics basically for scaling existing verification techniques and making the algorithms more efficient. And a lot of that sort of intersects with general algorithms research on just how to make things more efficient. So yes, I would say it is a big problem that people are actively working on.
I was curious about the notion of realizability here. It was more strict than I would have expected, because I would have expected realizability just to be, can you realize a strategy that meets the specification? So when we had Z greater than Y, I think it was, Y or Z greater than X, why could we not, why do we need that this can always be, this needs to always be true? Why can't we just say, oh, well, yeah, sure, I'll make Z 1,000 times what X was,
Yeah.
and then I'm always safe, and this is realizable because I found a strategy that.
Yes, so I've also studied the variant of the problem that, mathematically, you basically just weaken it to a subset inclusion in one direction. Yes. And it turns out, yeah, but that that can be derived from a solution to the stricter form.
But why do we care about the stricter version of this? In terms of embedded or distributed systems, is there something that it's more natural to care about the stricter version, and that's why we care about? Because I would think, well, I just need one solution, and one solution is good enough for people.
Right. So the reason we care is from an applications perspective, you might have a protocol that serves multiple possible functions in a non-deterministic way, let's say, and you would want to ensure that an implementation can also satisfy all those functions and can just sort of adversarially pick a subset that is easy to perform. Mm-hmm. I would say that's the motivation on a practical side. And then from a theoretical side, the two solutions are tightly related once you have a solution to the stricter one. Also, I would say this is a strange instance somewhat of a synthesis realizability problem, because in some sense, the problem is fully specified, right? You're not sort of learning from examples, or there's no partial inductive inference or anything like that. It's that the intended behaviors of each participant are fully contained in the spec itself. And you just need to check whether, when you distribute it in a pure way, that no additional behaviors arise.
Looks like we have a question on Zoom, which is a somewhat lengthy question. Simon, would you like to unmute and ask your question, or would you like me to ask it for you?
Sure. So I think at the end of the talk, what you were saying.
Why don't we hear you? We're supposed to hear you. We press some buttons and see if we hear you, and then if that doesn't work, we'll back to reading your question. Right, we can hear it through your. I suppose we can make sure we don't. All right, I'll read Simon's question. Sorry for not having the settings exactly right. So Simon Locke says, I want to ensure that I understand what you're saying at the end of your talk. I think that you're saying that this, where this goes with respect to AI LLM coding systems or AI generated code, is that we want to essentially build entirely new languages or development environments or runtime environments to guarantee correctness. And one way that you can get this done is to use fine automata. If that's what you're saying, I'm curious as to how this relates to expressing the rules that the automata are checking in English-like or human language, considering, for example, that Ruby has a strong following because it's language-based and would be interesting. I guess it's a question from really more generally about going from language-based specifications to actual implementations and proofs of correctness, and to what extent the language models can help bridge that gap.
Yeah, so there are two works that come to mind for this pipeline of you have some natural language intention and you have a formalism, let's even fix it to be automata, and then you're solving the problem in automata land. So from natural language to formalism, okay, it's not either of these two, but I know of works that take natural language intensions for something you want to prove in something very simple like propositional logic, let's say. So you have some atoms, P, Q, and R, you know some facts about them. You want to prove a formula that's in propositional logic. So people have designed ways of using LLMs to translate these formally into propositional logic formulas. So that's the first step. The second step, a great example is folks at Cornell have been developing this automata tool for determining, given a contract, so a legal contract that has a set of rules, let's say like a tenant contract. These are formalized as languages, and I as a user can say I have a query. Let's say I want to know whether my contract is consistent with me being able to dog sit my friend's dog in my apartment for 2 weeks. So this is, everything is translated into state machines. I believe not by LLMs, but manually. And then the problem of checking consistency of some query with the contract is reduced to a problem of language membership for automata. So there are sort of these different ways that the steps in the pipeline can be achieved.
And so far, though, it's open to actually connect all the steps into a working solution where you get LLM generated code that goes from a spoken specification to a proof that the code satisfies that specification, or are there limited areas in which that full pipeline is working?
I don't know of a work in which that full pipeline exists, but it might already exist.
Great, thank you. All right, any additional questions? All right, please join me in thanking Elaine again. Also, for those of you both here and on Zoom, if you would like to come speak to Elaine at 3:30 p.m. over cookies, we have a cookie break at 3:30 on the 5th floor, room 514, which is the open space on this side of the floor in Milstein. If you're a Columbia person, you can get in with your Columbia ID as well if you're on Zoom. So please feel free to join for cookies and more conversation then. And thank you all for joining.